Today we are going to learn an important spectroscopic technique, that is electron spin resonance spectroscopy. Electron spin resonance spectroscopy, or ESR spectroscopy. You know, some molecules like NO or something like O2 or NO2, etc. These molecules have unpaired electrons, right? Unpaired electrons. Unpaired electrons. And not only that, you have learned some complexes like FeCN 6 times 3 plus. Okay, the complexes of this type also have this type of unpaired electrons. And what is particular with the unpaired electrons? If the electrons are paired like this, then the magnetic moment or spin magnetic moment of one electron will be cancelled by the other electron. So there will be no net magnetic moment in this case. No net magnetic moment in this case. And because of this, it will not interact with an applied magnetic field. It will not interact with the applied magnetic field. But what do you expect if the molecules or species are containing unpaired electrons, one unpaired electron or more than one unpaired electron? In these cases, each unpaired electron will have its own spin angular momentum, and this spin angular momentum will generate the spin magnetic moment, and this spin magnetic moment can interact with the applied magnetic field. So in this case, there will be a net magnetic moment due to the electron spin, and this net magnetic moment will interact with the applied magnetic field. For example, let me write it as BZ. So this is something different from what we learned in the case of the paired electrons. So this type of species means the molecular species or ions or radicals or complexes which contains unpaired electrons in its orbitals will have a net magnetic moment, and they will interact with an applied magnetic field. And it is this property that we are going to harvest in order to get the electron spin resonance spectrum. And this technique is called the electron spin resonance spectroscopy. Normally it is also called electron paramagnetic resonance spectroscopy, EPR, electron paramagnetic resonance spectroscopy, because these species which contains unpaired electrons, they will be paramagnetic in nature. The electron spin, if they are unpaired, the species is going to be paramagnetic, and because of that, this technique can also be called EPR. So these two terms, ESR or EPR, these two terms you can use synonymously. Okay, and now we are going to learn the principle of ESR spectroscopy. It means how the ESR spectrum will originate from the molecular species containing unpaired electrons, or radicals containing unpaired electrons, or the complex ions or complexes containing unpaired electrons. That we are going to learn next. So the principle of ESR spectroscopy. And if you are considering the electron as a particle, why not? Electron is a particle. The electron was first proposed as a particle by J.J. Thomson, right? J.J. Thomson proposed that electron is a microscopic particle, and later on it was proved by his son J.P. Thomson that electron is a wave. Both of them got Nobel Prize. J.J. Thomson, he got a Nobel Prize for discovering electron as a microscopic particle. And G.P. Thomson, the son of J.J. Thomson, G.P. Thomson got the Nobel Prize in order to prove that electron is a particle. The first one got the Nobel Prize for the second one, G.P. Thomson got a Nobel Prize for proving that electron is a wave. So J.J. Thomson got Thomson, J.J. Thomson and G.P. Thomson. Okay, sorry for the spelling mistake. So J.J. Thomson proved that electron is a microscopic subatomic microscopic particle, and G.P. Thomson proved that subatomic microscopic particle can be a wave as well. Both of them got the Nobel Prize. So, okay, that is not our discussion anyway. And let us consider the electron as a particle for the moment. And this electron is having a negative charge, right? And the negatively charged electron is having a spin motion. Electron has a spin motion. And because of the spin motion, electron will have a spin angular momentum. The spinning particle will have a spin angular momentum. So electron will also have a spin angular momentum, and this spin angular momentum is determined by the spin quantum number. So the spin angular momentum I is equal to root of s into s plus 1 into h divided by 2 pi, where s is the spin quantum number of the electron. Electron can have the spin quantum numbers plus or plus or minus half. So s is equal to half in this case. Root of s into s plus 1 into h divided by 2 pi, where h is the Planck's constant. So this is the spin angular momentum, right? Spin angular momentum. And because of the spin angular momentum, the spin angular momentum will generate a magnetic moment. Why it is so? Because electron is a charged particle. Whenever a charged particle is spinning, associated with that spin, there will be a magnetic moment. Whenever a charged particle is spinning, no matter it is positive or negative, okay, whenever a charged particle is spinning, associated with that spin motion, there will be a magnetic moment also. So electron is a negatively charged particle, and electron is spinning, and it can be either clockwise spin or a counterclockwise spin if you are considering electron as a particle. Then associated with this clockwise or counterclockwise spin of the negatively charged electron, there will be a magnetic moment. And the direction of the magnetic moment will depend upon whether the electron is spinning clockwise or anti-clockwise. Okay. So electron will have a magnetic moment. Magnetic moment means electron can act like a tiny magnet. And this magnetic moment mu of the mu is equal to q divided by 2m into I. Okay, this is actually a general equation. Magnetic moment mu is equal to q by 2m into I, where q is the charge of the particle and m is the mass of the particle and I is the spin angular momentum of that particle. Okay, this is a general equation. It is applicable for not only the electrons but for any particles, okay, having some charge. It can be the neutron, it can be the electron, not neutron, it can be the nucleus or it can be the electron. Okay. Nucleus in the case of the equation NMR spectroscopy. Now we are going to apply the same equation for the electron. So the magnetic moment of the electron mu e, in the case of electron we can call it as mu e, that is the magnetic moment of the electron, that is equal to q. In the case of electron, q is equal to minus e, because electron is a negatively charged particle, divided by 2me, where me is the mass of the electron, into I is the angular momentum, that is I. Okay, so I is equal to root of s into s plus 1 into h divided by 2 pi. Root of s into s plus 1 into h divided by 2 pi. Okay, that is the magnetic moment. And the unit of this one is ampere meter square, or you can say joules per Tesla. Okay, 1 ampere meter square is equal to 1 joules per Tesla. So you can express this either in ampere meter square or in joules per Tesla. So here the magnetic moment of the electron is equal to minus E by 2me into h divided by 2 pi into root of s into s plus 1. So let me write it like minus E h divided by 4 pi me into root of s into s plus 1 joules per Tesla. This is the magnetic moment. And I got this equation by considering that electron is a spinning particle. Electron is a spinning particle. Okay, particle, that is important. And I assumed that the charge of the particle is q and the mass of the particle is m. That equation only I applied for the electron. So in this equation, electron is purely considered as a particle. But we know that electron is not only a particle but a wave as well. Particle is localized, but wave is delocalized. Electron can be localized and delocalized at the same time. This is a very difficult idea to understand. If you want to understand, you can go to my channel. There I am describing how this can be understood. Okay, and that is not the subject at this moment. And here we have to consider that the assumption that the electron is a spinning particle, that assumption is not that much valid, not 100% valid, because electron is something else other than the particle. It is a particle, at the same time it is something else. It's a wave also. So electron is something else. So in order to incorporate the real nature of the electron, let me introduce a parameter here, and this parameter will balance the error. Okay, so let me introduce a parameter G, and G E h divided by 4 pi me into root of s into s plus 1 joules per Tesla. So the magnetic moment of the electron is equal to minus GeH divided by 4 pi me, and I can write it again like minus G into beta in the root of S into S plus 1 joules per Tesla, where beta is equal to EH divided by 4 pi me. Here you have to be very careful. This E is considered as a positive quantity. Okay. So beta is equal to plus EH divided by 4 pi me. Do not substitute a negative charge here. Okay, negative charge of the electron. You have to consider it as a positive quantity. So beta is equal to EH divided by 4 pi me. If you are substituting the value of electronic charge, Planck's constant, and the mass of the electron, you will get the value of beta as 9.274 into 10 raised to minus 24 joules per Tesla. Okay, that's the value of beta. And this beta is called a Bohr magnetron. And here this new parameter G, which we introduced, and this new parameter G is called the gyromagnetic ratio. Gyromagnetic ratio. And for a free electron, The value of G gyromagnetic ratio is 2.0023. That is the value of G for a free electron. So we have the equation mu E, magnetic moment mu E is equal to minus G, mu E is equal to minus G beta root of S into S plus 1, where G is the gyromagnetic ratio whose value is 2.0023 for a free electron, and beta is 9.274 into 10 raised to minus 24 joules per sector, which is a positive quantity, and it is called a Bohr magnetron. So now we know that electron has a magnetic moment. And now, if we are considering the orientation of this electron's magnetic moment or electron's spin angular momentum, we have to adopt some quantum mechanical considerations. Let us consider the orientation of the spin angular momentum I of the electron. What is I actually? I is equal to root of S into S plus 1 into H divided by 2 pi. This is a spin angular moment. We wrote it in the beginning itself. Spin angular moment. And what about the orientation of this spin angular momentum whenever we are applying a magnetic field? We are going to apply a magnetic field, and in this magnetic field, this is the direction of the magnetic field. So actually this magnetic field has been created by using a horseshoe magnet. Okay, horseshoe magnet, you know what is horseshoe magnet. It will have the shape like this, like this. Okay, so it will be like this. The magnetic flux lines will be like this, or magnetic lines of force. Generally, the magnetic lines of force inside the magnet are from south to north. The magnetic force of lines inside the magnet are from south to north. So if you are considering a bar magnet here, and if this is the south pole, and if this is the north pole, and if you are considering the lines of force inside this magnetic field, conventionally we are taking the direction of the lines of force inside the magnet as from south to north. So when it emerges out of the magnet, it will come like this. It will come like this. So if you are considering the direction outside the magnet, it will be in this direction. It will be from up to down. But inside the magnet, it will be from down to up. Okay. So the convention is that inside the magnet, the lines of force are from south to north. So in this horseshoe magnet also, you have to consider the same way. The lines of force are from south to north. You can consider this as the south pole and this as the north pole of the horseshoe magnet. So inside the magnet, the lines of force will be like this, like this. So the direction will be like this. It will be like this, from south to north. Okay. So when you are considering the lines of force outside the magnet, means in this area, the magnetic lines of force will emerge out of the north pole and then it will go to the south pole. So it will be like this, whatever I am showing here. So if I am going to show only this part of the horseshoe magnet, this is the south pole, means this portion, and this is the north pole of the horseshoe magnet, north pole of the horseshoe magnet. And if you are considering the lines of force between this north pole and the south pole, it will be in this direction. It will be like this, right? The lines of force will be in this direction. In this direction. Means it will be from south, it will be from north to south because it is external to the magnet. Okay, it will be from north to south. So we are going to place the electron in such a magnetic field. We are going to place the electron in such a magnetic field. So in order for the simplicity, let me show only the direction of the magnetic fields here with only one line. So let me remove the second line of force. So this is the direction. Okay, and we are going to place an electron in this magnetic field. And I said that whenever the electron is placed inside the magnetic field, its direction, the direction of its spin angular momentum will be restricted. The spin angular momentum I will have only certain possible directions, only certain restricted direction. The direction is so chosen that we are going to adopt a quantum mechanical restriction, and this quantum mechanical rule says that the direction of the angular momentum, direction of the spin angular momentum in a reference direction will be half multiple of half integral multiple of h divided by 2 pi. Means you suppose that this is the spin angular momentum. Spin angular momentum is a vector and this is represented by I, and its value is root of s into s plus 1 into h divided by 2 pi. Okay, so if you are considering the component of this angular momentum in the reference direction, that component of the angular momentum in the reference direction should be either plus half into h divided by 2 pi or minus half into h divided by 2 pi. So what we can do is here you have 2 pi here, 2 pi here, 2 pi here. You have 2 pi for 2 pi in the expression for the spin angular momentum, and you have h by 2 pi, h by 2 pi, h by 2 pi in the expression for the components as well. So we can consider h by 2 pi as a unit in the whole drawing. Okay, so all these are the units of h by 2 pi. Okay, so if I am marking as half here, it means that it is half h by 2 pi. If I am marking here minus half, it means that it is minus h by 2 pi, because one unit is h by 2 pi in this case. So I can just remove h by 2 pi from here, because this spin angular momentum is also drawn in the h by 2 pi units. So this length is root of s into s plus 1 units. One unit is h by 2 pi. So when you are taking the component of this one here in the z direction, this is a z direction, means the direction of the line of force of the magnetic field. So when we are taking the component of this one in the z direction, that component is half unit, means it is half h by 2 pi. And if you are considering another direction like this, and this is also I is equal to root of s into s plus 1 units. Okay, but its direction is different, magnitudes are same but direction is different. And if you are considering the component of this vector in the z direction, it is minus half. It means it is minus half into h by 2 pi. Okay, so this is the quantum mechanical restriction. The quantum mechanical restriction is that the component of the angular momentum in a reference direction should be half integral multiples of h divided by 2 pi. That is the quantum mechanical restriction. So this angular momentum can orient the angular momentum vector of the electron, the spin angular momentum vector of the electron can orient only in two directions in the space, because only in these two directions its a component will be half integral units of h divided by 2 pi, half integral multiples of h divided by 2 pi. In any other direction, it will not be a half integral multiple of h divided by 2 pi. So this is a quantum mechanical restriction. This is a spatial restriction or directional restriction. So now we have the components of the angular momentum. These components can be called as Iz, because it is a component in the z direction. Here the z value is half, and here the Iz value is equal to minus half. Okay, now what about the magnetic moment? What about the magnetic moment? Because we already learned that associated with the spin angular momentum there is a magnetic moment, and the expression for the magnetic moment is equal to minus g into beta into root of s into s plus 1 that we already learned, right? So the magnetic moment, the direction of the magnetic moment actually is in the opposite direction of root of s into s plus 1 vector. If you are considering this root of s into s plus 1 is the magnitude of a vector, then the direction of this vector will be opposite to the direction of the vector with the magnitude root of s into s plus 1 because there is a negative sign. So the component of Iz is like this. This is Iz. From here to here, this is Iz, and that is Iz is equal to half. And this is another Iz which is minus half. These are the direction. This is upward and this is downward. And in this case, what will be the direction of the component of the magnetic moment? We can take the component of the magnetic moment also in this direction. And what will be the direction of the component of the magnetic moment? And that magnetic moment's the component of magnetic moment's direction will be opposite to the direction of Iz. So if Iz is equal to downward, the corresponding magnetic moment's component will be upward. So this is the mu Z's direction corresponding to Iz is equal to minus half. This is mu Z's direction corresponding to Iz is equal to minus half. That is upward. And what about this one? This Iz is upward from down to up. Therefore, the corresponding magnetic moment component will be downward. So this is mu Z, that is correspond the magnetic moment component in the Z direction corresponding to Iz is equal to plus half. So now you look at these directions. One is upward and one is downward. So magnetic moment is that is the extent of the magnetic dipole strength, right? So if you consider electron as a magnetic dipole, and this is one magnetic dipole and this is another magnetic dipole, this is the direction of the magnetic dipole, and the direction of the magnetic dipole is from south to north. Therefore, this is south of the magnetic dipole of electron, and this is north of the direction of the magnetic dipole. Okay, so let me draw it in another color. Let me take it as red. So this is south pole and this is north pole because magnetic lines of force inside the magnet is from south to north. But when you are considering electron as this type of a magnet, this is south pole and this is north pole. So these magnets are inside this horseshoe magnet, right? And here, if you are looking at these magnets, the south pole of this magnet is near the south pole of the horseshoe magnet. So south pole and south pole will repel each other, and this will have a higher energy. So this is corresponding to high energy situation. So this mu Z corresponds to high energy situation. And what about this mu Z? That is, in this case, south pole is near the north pole and north pole is near the south pole of the horseshoe magnet. So south pole loves north pole and the north pole loves south pole. This is a low energy situation. So this type of arrangement is a low energy situation. So we can have two energy situations when we are placing an electron inside a magnetic field. Either that electron can orient in a high energy situation, or that electron can orient in a low energy situation. Okay, and what about this interaction between this magnetic dipole moment and the external magnet? So if the external magnetic field strength is mu Z, external magnetic field strength is B Z, Okay, Bz. Since it is in the z direction, I am taking it as z, Bz. And what about the interaction between this external magnetic field and the magnetic moment of the electron? And this interaction is or energy interaction is equal to Bz into mu Z. Okay, Bz into mu Z. That is Bz multiplied by the component of the magnetic field in the Z direction. That will be the interaction or that will be the energy. Okay. So what is the difference? So these two will have a different energy. This is a high energy situation and this is a low energy situation. They have different directions. Okay. So what is the difference in energy between these two? Here in both cases mu z is different because mu z actually depends upon I z, right? And now we can give the expression for interaction or energy, that is equal to Bz into I mu z in this case is G beta Iz into Bz, right? G beta into Iz, G beta into Iz. Okay, so here Iz actually is root of S into S plus 1's component. Iz is the component of root of S into S plus 1. Therefore, mu Z will be G into beta into Iz, because we already learned that mu is equal to root G. Sorry, there should be a negative sign also. Negative sign also. So mu is equal to minus G into beta into root of S into S plus 1, that is mu, magnetic moment mu. What about the component of the magnetic moment mu Z? That mu Z is equal to minus G into beta into component of S root of S into S plus 1 in the Z direction. What is the component of root of S into S plus 1 in the Z direction? That is Iz. That is why I have written like Iz here. That Iz can be either plus half or minus half. Therefore, mu Z depends upon the Iz. Either it is plus half or minus half. Okay, that depends upon the mu Z depends upon that values. So that is why I have written interaction is equal to Bz into mu Z. Therefore, this is equal to minus Bz into G into beta into Iz. Okay. So that is the energy of a particular situation corresponding to any Iz situation. So what about the energy difference? What about the energy difference? What about the difference between these two Iz and these two Iz have a difference of 1. This is minus half and this is plus half. What is the difference between plus half and minus half? 1. Okay. So what about the energy difference between these two situations? The energy difference delta E is equal to that is a modulus. Okay, I am taking the absolute value of the energy difference, that is modulus minus G into beta into Iz into Bz. That is the one particular situation corresponding to any Iz. Okay, minus the another situation corresponding to the next Iz value, that is minus of G into beta into what about the next Iz? What is the difference between one Iz and other Iz? That is 1. So the next Iz can be written like Iz minus 1 into Bz. Okay, Bz. You can write Iz plus 1 also. That is not going to make any difference because we are going to take the modulus of this one. So that is equal to modulus of, we can take it as positive, right? Minus of minus, that is equal to positive. That is equal to G into beta into Bz into, these are common factors, into Iz minus 1 minus Iz. Okay, Iz and Iz are cancelled, and what is remaining is that is modulus of minus G beta into Bz, okay, that is equal to modulus G beta into Bz. Okay, so that is the difference in energy between two electronic spin states. That is the difference in energy between two electronic spin states. So this is the difference. These two spin states will have this difference. The energy difference between these two spin states, delta E, is equal to G beta into Bz. That is what we have proven. Now, if an electron is in this energy situation and if it is getting enough energy, then it can make a transition to the higher energy situation just by absorbing the energy which is equal to G into beta into Bz. So this energy is usually absorbed in the form of a photon. So we can calculate the energy, the frequency corresponding to that photon. So the frequency corresponding to that photon is equal to the difference in energy divided by Planck's constant h. Okay, because h nu is equal to delta E. So delta E by h is equal to G into beta into Bz divided by h. So if this frequency is given to the electron in the lower energy state, that electron will absorb this frequency or absorb this photon, and then it will make a transition to the higher energy situation. It will make a transition to this higher energy situation. Okay, so corresponding to that, there is an absorption of energy, and this is what is leading to the ESR spectrum. Okay, this is what is leading to the ESR spectrum. So if we are calculating this frequency, let us operate this experiment at around 0.34 Tesla, 0.34 Tesla, and we can calculate what is this frequency at 0.34 Tesla. Okay, let us calculate this frequency. That is equal to G. G in the case of a free electron is 2.0023 into beta. Beta value is 9.274 into 10 raised to minus 24 joules per Tesla. Okay, into Bz. Bz is a magnetic field strength, that is in our case it is 0.34 Tesla divided by Planck's constant, that is equal to 6.626 into 10 raised to minus 34 joule second. Okay, so what is this value? And you can calculate this value, and that is equal to 9528.482 megahertz. Okay, that's the value. Actually, you will get this value in hertz first, then you can convert this to megahertz. Okay, how you are getting the value in hertz? Because joule and joule are cancelled, and Tesla raised to minus 1 Tesla are cancelled. Then what is remaining? Second in the denominator. So when it goes to numerator, it will be second inverse, and second inverse is equivalent to hertz. Okay, and you will get the value in hertz, and then you can convert it to megahertz. Okay, so in order to convert that to megahertz, you can just multiply this with 10 raised to minus 6. Okay, then you will get it in megahertz. So this is the value that you are going to get, 9528.482 megahertz. So that is the resonance frequency for the free electron in a field of 0.34 Tesla. 0.34 Tesla. So in this 0.34 Tesla, we expect that the free electron will jump from its low energy situation to the higher energy situation by absorbing a photon having the frequency 9528 into 4.482 megahertz, and this frequency falls in the microwave region of the electromagnetic spectrum. Okay, so if you are giving the sufficient microwave photon to the electron can make transition, and that will give the ESR spectrum. And now you understand how ESR spectrum is being generated. The first the criteria is that only the molecules having unpaired electrons will give the ESR spectrum, and this ESR spectrum will be obtained in the microwave region, and actually it depends upon the field strength. Okay, so if you are measuring the ESR spectrum in terms of the frequency, that frequency will definitely depend upon the field strength, and this frequency is obtained for 0.34 Tesla. If you are applying another field strength, you will get another frequency. So for a particular electron in any molecular species, you will get different values of frequency for different field strength. That is not good, right? That's very annoying. So in ESR, we are not expressing this resonance in terms of frequency. Rather, we are depending upon the G value. We are depending upon the G value. So what about G? And from this expression itself, because we have the expression delta E by H is equal to G beta into Bz divided by H. From this one, G is equal to delta E by beta into Bz, right? Delta E by beta into Bz. So G is equal to delta E. uh, G is equal to, see this one. Sorry. We have nu is equal delta E by H is equal to G beta into Bz. Therefore, G is equal to delta E by beta into B0. We can write like that. G is equal to delta E divided by beta into Bz, and that is equal to H nu. That is equal delta E is equal to H nu divided by beta into Bz. Beta into Bz. So we can get to G like this, and this G actually is a constant for a particular nucleus, particular electron. Okay, for a particular electron it is a constant. For a free electron, you already know the G is 2.0023, and depending upon the environment, this G will change. Okay, actually almost all the free radicals and some crystals have the G factor, which is very close to the G factor of this, close to the G factor of the free electron. Free electron G factor is 2.0023, and if you are taking the G factor of some radicals or some ionic crystals, okay, the G factor will vary only plus or minus 0.003. That's all. Why is it so? Because in radicals, if you are taking a radical, you can see that this electron actually will occupy an electron which will encompass all the atoms in that molecule. That orbital will be belonging to all atoms, almost all atoms in the molecule. And this electron will be free to move in this big orbital which will cover almost all the atoms. So it can be actually considered as almost like a free electron, and it is not confined to a particular atom or particular orbital. It is confined, it is free to move in a big orbital which is covering almost all the atoms in the molecule. So that is why the radicals will show a G factor which is very close to the G value of the free electron itself. But you can see that in some ionic crystals, okay, the G factor can vary. Some ionic crystals, it can vary from 0.2 to 8.0, a very big range, right? 0.2 to 8.0. So these values are reported, and here the difference is that the unpaired electron is contributed by, and it belongs to, a particular atom in the lattice. The unpaired electron belongs to a particular atom in the lattice, and that is why its movement is restricted. It is not like a free electron. So that is why it can give a wide range of values from 0 to 0.2 to 8.0. Okay, so this is possible. So the parameter that we are using in the ESR spectrum is not the frequency but the G parameter. And I hope you understood this much of the ESR spectrum. And I hope you understood the principle of this ESR spectrum. And we will see more things in the next classes. And if you have any doubt, feel free to ask me. And thank you for watching and stay tuned.